Okay, so section 14.2, I'm going to stop talking about exponentials for the minute and we'll come back to exponentials in a minute and it'll be clear why. Okay, so here's something we're interested in. We've got this new process called differentiation that we learned about in chapter 12. And whenever we've got a mathematical process, it's interesting to find something that doesn't make a difference. So the first thing we learned probably in maths was addition, right? And when we're doing addition, 0 is an important number, because if you add 0, nothing happens. Anything plus 0 is what you started with. And that means that 0 is kind of special when it comes to addition. It's actually called the additive identity, if you want the technical term for this. With multiplication, 1 is quite a special number, because if you times by 1, nothing happens, okay? So it's an interesting thing in maths to have, you know, the whatever new thing we've invented, whatever new process we've invented, is there anything where it wouldn't sort of change, all right? Is there anything that would leave alone our input? And these are examples of that. So with differentiation, is there a function where if I start off with the function and I put it through the process of differentiating, then I get out the function that I started with, okay? Now that would be quite an interesting thing, wouldn't it? So let's think of what it would look like. Well, the function tells me the y value, it tells me the height of the graph. So let's pick a height 1 on the y-axis just to give ourselves an easy starting point. That would mean if the gradient function, if the derivative is going to be set the same as the y value, remember this is what I'm wanting, y equals dy by dx. The function is equal to the gradient. This is the height on the y-axis, this is the gradient of the graph there. So here, the height on the y-axis is 1, so the gradient would have to be 1. When the y-axis gets to 2, then I want the gradient to be 2. When the y-axis gets to 3, I want the gradient to be 3. So basically, the higher up the y-axis I go, the steeper it gets, all right? So we want this sort of shape. And then when I get lower on the y-axis, where y equals a half, I want the gradient to be a half. Y equals a quarter, I want the gradient to be a quarter. So slower and lower, shallower and shallower, and the closer I get to 0, the closer the gradient gets to being horizontal. So actually, what I'm looking for is something that has the same sort of shape and the same sort of properties as an exponential graph. And exponential graphs only have outputs on positive y numbers, right? So, but never mind that. We can input any x value, and we get this. We don't get any negative y values, but let's not worry about that for the moment. If we could find this graph, that would be a good start, wouldn't it? That'd be an interesting thing to look at mathematically. And because it's got this sort of shape, we're thinking, well, maybe it's an exponential. If it is an exponential graph, then that would be something of the form y equals a to the power of x. So if we can just find this a, what's the number that we've got to put in so that we get this property? And it turns out that that's exactly what happens. There is a number. And if you try it, then the number turns out to be 2 and a bit, right? It's 2 and it's in the textbook on page 314, 2.71828. Oh, for anyone that likes this sort of thing. E is named Euler's number and is one of the sort of really important mathematical numbers. And another one being pi, you know, and people often say sort of 0, 1, E, pi are important numbers, and they represent sort of some of the major processes. And just interestingly, we're learning about the number E for the first time on page 314, which is the first 3 digits of pi, isn't it? So there we go, that's fun. E named E for Euler, who was a famous German mathematician, so we call it Euler's number. And E is the number 2.71828 and a bit, all right? So this number is 2 and a bit, and it is the number which gives us the exponential curve, which is sort of steep enough and not too steep, so that when you differentiate it, the y value is equal to the gradient, okay? In other words, if f of x equals e to the x, the derivative of that function is also e to the x. Or if you like the y notation, if y equals e to the x, dy by dx equals e to the x. So it's the easiest function to differentiate because nothing changes when we differentiate. It's useful in lots of ways. For the moment, it's not necessarily clear to you what those ways are, but the further through you get, the more you'll see how useful e is as a number. Now, they've decided to put this into the AS syllabus and put it on the start of the course, in the first half of the course for the A level in the year 12. Now the problem is we can't do much with this information unless we learn a bit more calculus. So they've decided what they're going to do is just give us a fact without really explaining it. And I'm going to follow suit. I'm not going to explain this fact, but I will say to you, when you get to the year 13 course and look at the differentiation on there and you look at the chain rule, then we have an explanation of this fact. So for now, they tell us this. They tell us if we've got y equals e to the 4x, for example, then the derivative of that isn't just e to the 4x, but it is 4e to the 4x. Okay, so if you got a number up here, and it's written in the textbook with a k, so I'll do it with a k. If we got e to the k times x, then if that's the function, the derivative, you want it to be e to the kx, you want it to be the same thing, but because it's not just e to the x here, we've got to make a slight adjustment. That slight adjustment we've got to make is to put the k in the front. There is no explanation of that in the book. I am not explaining it to you now. That's just something you're going to have to believe us on for the moment so that you can answer the questions. You shouldn't be able to see why that is true. Well, I mean, maybe you think you can see why that is true. I don't think it's an intuitive fact. You can get a bit of an idea if you think about if this is e to the x, then e to the 4x would be a squash in the x direction, so it would make it steeper. So the gradient would have to increase a bit, and you can get a sort of intuitive idea that way if you really want to. But for the moment, we're just telling you, trust me, this is the case. So that will allow us to do example 3, differentiate those things with respect to x, and it's straightforward enough. I don't think we need to go through that one. Example 4, you just have to remember that e to the x, e is just a number, so y equals e to the x just looks like this. So y equals e to the 2x is a transformation of that graph. And in this case, we've times by 2 sort of inside the bracket style. All right, so that's a squash in the x direction, and so on for the rest of the ones in that example. So that's all we really need to know in exercise 14b. We're just introducing you to this new number e. And in example 14, in section 14.3, we will talk about it a bit more.